So I wanted to take just a bit and go through a verification. It's not really a proof. I'm not going to do official formal proof. I'm going to sort of just talk through a few notions on how you would actually verify the power rule that we've developed. So if you recall, the power rule says this: the derivative with respect to x of x raised to the n is equal to n times x raised to the n minus 1. So some specific examples of this. A specific occurrence might be, suppose f of x is equal to, let's say x to the 9th. Well, this is the power rule with n is equal to 9. And so from that, we can imply that the derivative of that is what was the exponent becomes the coefficient. So this is 9. And then x raised to the how much? Well, the exponent becomes the original exponent minus 1. So in this case, 9 minus 1 is 8. So the derivative of x to the 9th is 9x to the 8th. Now, it turns out this is true for all values of n. The verification, again, I'm going to work is, I'm only going to deal with the natural number circumstance. But it also is true for, let's say, for example, fractions. So if f of x is, let's say, x to the 1/3 power. Remember, that might have arisen by having the function third root of x. Third root of x is the same thing as x to the 1/3 power. So this implies the same thing as before. The derivative is the exponent becomes the coefficient, and the new exponent is the original exponent subtract 1. 1/3 minus 1, or 1/3 minus 3/3 is negative 2/3. And so that's the derivative. Suppose, I'll just change some letters. Suppose g of x is, let's say, x to the negative 3. Then it's the same rule. N is now negative 3. So negative 3 is now the coefficient. X raised to, I need negative 3 minus 1. Remember, that's negative 4, not negative 2. Now, another thing to bear in mind, suppose I have h of x is equal to 1 over x to the 6th. Now remember, what we need to do is rewrite this into a form that the power rule can use. And so we're going to rewrite this as x to the negative 6. Many of you some of you may have overlearned this in basic algebra. Many of you have learned that if you write x to the negative 6, your instructor said that was wrong. If you write this as 1 over x to the 6, they said that was right. That's not the correct way to view it. The way to view it is each of them are correct. It's just sometimes this is preferable, sometimes this is preferable. In this particular case, it's preferable to write this without the fraction, because now this is the power rule with n equal to negative 6. And so we follow the same pattern here that we followed up here with this g function. So this implies that h prime of x is given by negative 6, x to the, I need negative 6 minus 1, that's negative 7. And so these are all instances of the power rule. Now what I'm going to do is go through a verification of the power rule. Again, it's not really a proof. This is more of a sort of a seeing where the proof comes from than it is an actual proof. And I'm only going to consider the scenario where the exponent is a natural number, not where it's a fraction or a negative number. And so what we're going to do is this. Let's let, for ease of notation, let's suppose my function is f of x is equal to x to the n. And so by the definition, we have the derivative of x, or a derivative of f of x is equal to the limit, as delta x goes to 0, of f of x plus delta x minus f of x all over delta x. Well, in this case, f of x is x to the n power. So group of f of this large expression is that large expression to the n. So this is equal to the limit, delta x goes to 0. This is x plus delta x raised to the n minus f of x is just x to the n. All right? And we need to expand this out using the binomial theorem. The binomial theorem says that when you multiply a binomial to the nth power, there is this procedure for multiplying it out. What I'm going to do is multiply this out sort of conceptually. I'm not going to write all the details in, but I'm going to get the idea across, because when I multiply this expression to the nth, what we get is x to the n, and then we get n is a coefficient times x to the n minus 1 times delta x. You'll remember that this first factor loses a degree each term, starting with n, then n minus 1, then x to the n minus 2, and so on down. But delta x gains a degree, starting with 0, and then first degree, then second degree, and so on. So what I'm going to write is, I'm going to write this conceptually. These are all terms with delta x squared or more. Now that is extremely unofficial. This is the basic idea. All these terms have delta x is increasing exponent each time. This is delta x to the 0, delta x to the first, and then we would have delta x squared, delta x to the third, to the fourth, to the fifth, and so on out. So all these terms have delta x, and again I'm writing this conceptually, delta x squared or more. That's very unofficial. And then we still have minus x to the n. Well, of course, negative x to the n cancels with positive x to the n. And so now what we're going to do is what we did in our work when we work with quadratics or cubics. All these terms have at least one factor of delta x. I'm going to factor out delta x. Now, if you do that, the question is, what gets left behind? Well, here, this n, x to the n minus 1, which looks familiar, that gets left behind. But then what gets left behind here? Well, all the terms in here have delta x to the second or more. So if I factor out delta x to the first, that leaves behind terms, all of them have delta x to the first or more. So these are terms with a factor of delta x or more, but they have at least one delta x. All that divided by delta x, and now that cancels with that. I'm running out of space, but we can see what's going to happen. Now evaluate the limit. As delta x goes to 0, everything here is constant with respect to delta x. So the limit of this constant is this constant, n, x to the n minus 1. But each term in this expansion has a factor of delta x, and as delta x goes to 0, each of those terms goes to 0. And so we're left with n, x to the n minus 1. So this power rule, it turns out, is a consequence of the binomial theorem that you may have discussed or learned about in a pre-calculus course or an algebra course somewhere. And so that's our power rule, and we will use this often and freely, and if you had a dime for every time you use the power rule over the next several semesters, you probably end up with, I don't know, $150, $200, because it's going to be all over the place. So that's, again, it's not a proof, but it's a rough idea of explaining sort of where the power rule comes from. This is not something I'm going to expect you to be able to reproduce, but I want you to sort of see the argument to get a feel for the kinds of arguments that go into working with these concepts in the calculus.